Yeah, so thank you for the invitation. It's a great session. A lot of what I'm going to talk about is probably going to be repeated, or maybe some of that you know already, but I think repetition in that aspect of replicability is important. So I'll do a quick historical perspective. Was Ioannidis right? I think that's the question. What is and are the problems? Are they more technological, or are they more methodological or sociological? And then is there a solution at all? So this is a slide I borrowed from Victoria Student, and saying that if you are not convinced yet that there is a problem of replicability in science, I think you're probably not reading the right papers and reading the right. Everyone is talking about it, and that's clear that we have a problem, and the question is, how do we solve it? So first of all, I'd like to come back to the reproducibility versus replicability. So reproducibility is mostly a computational issue, right? And that's all the Docker container aspect that Chris was talking about. And it has some statistical aspect, but it's mostly a computational issue. Replicability is really a statistical problem. And there is evidence that the reproducibility and replicability, actually replicability is impacted by our current statistical procedures. So if you look at the work from statisticians showing that p equal 0.05 is a weak evidence, or if you look at Ioannidis' theoretical arguments, you should be convinced by it. And statistics is not just like a method, it's also the practice of statistics, what you do with the method. So how do we study the practice? I mean, what the studies on the practice of statistics tell us? Well, if you look at Simon and Simonson, psychology, or more recent paper, you'll see that statistics are very poorly practiced. So anecdotal evidence number one, this is a study on unipolar depression. There's a lot of unipolar depression neuroimaging studies. This is a meta-analysis of all those studies, and what the meta-analysis shows is that across all those studies, there's absolutely no significant results. So basically, message number one, many papers being published with significant p-value, meta-analysis, after some work, and then you don't find anything. This is another anecdotal evidence, and if you, they're big like activation in the brain. If you look for anecdotal evidence, you will find them, right? So this is one with looking at the association of what you eat and the risk of cancer, and the studies showing that most of the food that you eat have actually either associated with an increase or decrease of the risk of cancer. And obviously, again, weak or not that weak p-values, like 0.05, 0.001, and the meta-analysis showing that this is not, there's nothing there, or very, very little there. So what's the historical perspective like? First of all, what's the p-value aspect? So it was introduced in 1925, so very, very long time ago. And as soon as it was introduced, it was starting to create problems. The Fisher conception was that this is something that is indicating something about the data under the null, right? And then there's the Neyman-Pearson conception, which is basically this is just a rule for making a decision. You choose your p-value threshold before your experiment, and then you just decide whether it's accepted or rejected, and that's it. You don't even look at the p-value. It doesn't carry any information by itself. Only the threshold you have decided on is important. So what is used today? Mostly the Fisher perception, and probably the Fisher aspect is much more less grounded than the Neyman-Pearson framework. So let me take the classical example of, I think this is a Westover questionnaire, and put to medical students. And the question was, okay, I've got two populations, I'm doing a test. The test is showing that there's a p-value of 0.05. Now, look at those possible response to the question. What does it mean? What does it mean? Look at those possible response. So is H0 false? Is H1 true? Is H0 probably false? Is H1 probably true? Is both 1 and 2, both 3 and 4, or absolutely, or none of the above response? So can I have a show of hands who thinks that the correct answer is number 7? 1, 2, 3, 4. Handful of people, right? This is the correct answer. So it does mean either you're very shy, you can't put your hands on, or you think that the correct answer is not number 7, which means we have a problem, right? If most of us still don't understand what the p-value means, we have a serious problem, because most of the papers are published using p-values. And that's also the answer of the medical students, that most of the number 7 has very few counts, and most of the people think that probably means that the H0 is probably true, false, and H1 is probably true. So what happens if a p is significant but study power is low? And you've seen some of the previous in the previous talk, the Button et al. Paper, and showing that the power of our studies, the sample size is too small and the power is low. So it means that we will get a low positive predictive value, which is the probability of our hypothesis, alternative hypothesis, the thing that we would like to be actually true and verify. Given that we have a significant test, that probability is going to be low. So it also means that if we have a small sample size and small power, we get inflated effect size. So I will find big t values, but those t values won't be big in the next sample size. And it also is important to recall that this probability of HA or H0, the probability that your hypothesis is true or false, is actually depending on what is the likelihood that before you do the experiment, that probability is true. You know, if I'm testing something which is very, very improbable before the test, then even if I find something significant, it is unlikely to be true. So let's take a simple and classical sort of a setting where this prior odds of H1 over H0 is about 0.2, so 5 times more likelihood of having the null hypothesis to be true compared to the alternative, and a p-value of 0.05. And then let's see what's and a power which is, let's say, 0.3, 0.4, because that's what Button et al. Has shown to be the median power across neuroscience studies. You'll get a positive predictive value, so that's a probability of the hypothesis to H1 to be true, to be around maybe 0.4, 0.5, something like that. So there's half a chance that even if your test is significant at 0.05, your alternative hypothesis is going to be true. And that's been shown again and again. So you see here in that slide, you see the publication, the year of publication on the x-axis, the effect size on the on the y-axis, and you'll see that those effect sizes are diminishing with the years, with the size of the sample sample here being represented by the size of the circles. So you start with like very significant results, small sample size, and then a few years later, zero sample size, no significant results. All right, not everybody believes in power. I've just told you power is super critical, but you do find people, and this is a reviewer of a grant, says, I'm skeptical that searchers of existing studies, so this is how you estimate power, is going to be interesting and for reproducibility of our scientific and for new interesting design. So if you have a new interesting design, then you can't estimate power, you can't do anything. I would very much have a coffee with that person and explain why we should do something different. What happens if P is not significant? The file drawer effect. It's been described by Rosenthal in 1979, so a long time ago. Most publications are only accepted if P is less than 0.05. It's hard to publish null result, and so on. If you do that, if you do a little search on PubMed, you'll see that the number of no evidence for something is like maybe 2,000. The number of evidence for something is like 300,050 or something like that. So it's a ratio of 1 to 500. But wait, are we actually testing things at the 0.05 level? There's a very strong evidence in many different fields of science, and I think in neuroimaging as well now, that we are not. Because of the flexibility of analysis, and described here in Simmons et al., we actually have a very inflated error rate. So that's another way of showing that with the Karp, Karp study. We're looking at the variability of the place of the maximum activation on the brain if you're varying the pipeline of your study. So if you're not testing at 0.05, then what is our positive predictive value? Well, then that's becoming really, really bad. Even with a power of 0.5, you have like a 0.25 probability of replicating or having the H1 to be true. And that's where maybe we are in that situation. Is that really happening? Can we make sure that, is it, I mean, I'm skeptical. Is it really happening? Let's do a study. And this is a study of biostatisticians being consulted for, on studies. And that study showed that there's very clear evidence of very severe violation, and that happened very frequently. So yes, it is the case that we are not using the statistics properly. This is the possible very dire situation described by Dorothy Bishop, where you start with a hypothesis, they have a poor study, then you do some poor power, you do some p-hacking, and then some, you find eventually something because of p-hacking, and then you just go on with that. You don't publish the thing that is not significant, and then you go on by doing some kind of hacking hypothesis after the result. And that's it possibly is a lot of our publication in that stage. So what are the solutions? I've got 3 minutes to give you the solution. They are either technical, and there's a number of things that possibly we could do, or they're social, or they're both. And I think obviously they are both. The technical, can we redefine significance? Can you use Bayesian framework? Can you do prediction framework? Social, can we work with the journals? Make sure that we ban p-value, maybe? We look at how we check things on how things were done in the publication, the registered report that Chris described, and so on. Technical, redefine significance. 70 very prominent scientists work on that Google document saying, okay, we should declare now that something significant is 0.005, not 0.05, right? Okay, it goes because it's in the Bayesian framework, it goes from a weak evidence to a fairly strong evidence. And I think that's interesting. Oh, right. Really? 88 less prominent scientists declare that this is not the solution, and we should instead, declare define exactly why we're using 0.05 or 0.05 and so on. So there's a number of reasons for that, and we're going to skip a bit of them. And obviously those Bayesian people say, no, absolutely not, we should, and so on. And the debate is there, and we're still debating on the p-value defined in 1925, and we still don't know how to use it properly. Registered report. I was struck and pointed to this thread in Twitter. You know that most of science is happening in Twitter now, and that's Chris Chambers, who is maybe one of the most prominent and possibly the inventor of the registered report in Cortex, and saying, okay, if you don't believe that a registered report is the right solution, that's because you don't believe there is a reproducibility problem. Well, Jack Gallant, which is has a strong opinion and sometimes very good opinion, says, no, absolutely not. I do believe that there is a problem with reproducibility, but what you should do is use better methods. It's just that those p-values are weak methods and they're not telling you much about the data and so on. So what we should do is use some greater evidence for small effects, require that the journals ask for more evidence, and so on and so on. Well, Dai has a good wisdom and says, even if you have to do that, the pre-registered report is going to help you identify the problems before they happen. And Tomasio saying, hey, even the predictability, the prediction framework is not the right framework. Even that, in that framework, most of maybe if you have a small sample, the studies won't replicate. So I think that's very important to see, and this last point by Thomas is actually very true. There has been already some evidence of that, and at that specific in this meeting, we've seen some of that. So what are other solutions? There was a psychological journal that actually wanted to ban entirely the p-values. They say, okay, you can put some p-values, we're going to erase those p-values before we publish your paper, right? And there was a Nature editorial, right? Nature is a serious journal, saying, okay, well, this is what they want to do. The closer to zero the p-value gets, the greater the chance of the null hypothesis is false. Who says that's a correct statement? Thank you. Nobody. That's not a correct statement. Even the editors of Nature don't understand the p-value, and then they correct the thing because some statistician tell them, you know, that's. So we still have a problem. We don't understand the p-value, right? It's not only you or me, or it's pervasive in the scientific community. So registered reports are a good solution. I think they should be used more and more. COBIDAS or best practices, getting some standard to ETH or more reuse of data, all those are really the important aspect that we should be working on. So I think Ioannidis was right. And you should reread the conclusion of this 2005 paper. And we should try to change the culture of how we do our statistics and the training aspect on the statistics as well. And thank you. I've got plenty of people to thank. And if you want to, if you're interested in reproducibility or your informatics project, come and see me. Thank you.